So it's nearly 30 years since I was introduced to the technique of scanning probe microscopy and scanning tunneling microscopy in particular. I was attending the European Biophysical Society Congress in Bristol in 1984 and had gone to the X-ray microscopy session to see how far they'd got along with that. As I came out of the session, I walked over to the next session in the watershed in Bristol with a chap from Switzerland, and to make small talk I asked him what he did, and he told me about this new microscopy technique involving bringing a sharp probe very close to the surface and measuring the quantum mechanical tunneling current between the probe and the sample. And I thought, it's going to be really hard to keep that mechanical stability. You need an angstrom or two separation, and as you scan over the surface, how are you going to maintain that? So I thought, that's not really going to be a starter. But I went back and checked his papers, and sure enough, he'd managed to get atomic resolution. Of course, that was Hani Röhrer, who, together with Gerd Binnig, were awarded the Nobel Prize in 1986 for the invention of the scanning tunneling microscope. And it was from that point on I changed my career from X-ray work to scanning probe techniques. So over the last 30 years, of course, there have been lots of highlights, and it's interesting how the field has never really settled down and matured. It's continually changing with new ideas and new techniques being developed and evolved. I mean, just going back to seeing atoms on the surface, the very first pictures was amazing. But then there were ways of looking at the tunneling spectroscopy, so you could look at the actual orbitals and the states within individual atoms. And then the work of Don Eigler at IBM in Almaden, able to move atoms around. That was extraordinary, and able to make quantum mechanical structures by arranging them in different shapes and looking at the standing wave formations within them. This kind of work is still outstanding, even probably, 20 years on. That's continued with Andreas Heinrich in the same lab, using atomic force microscopy in non-contact to image individual atoms and move them around, but now manipulating their spins, so it's possible to make little domains of antiferromagnetic structures, which might be a way of increasing the density of storage in magnetic devices. If you think about other types of atomic force microscopy, the invention of non-contact techniques and the early work of Franz Giesebel, the first person really to see, again, the 7x7 structure in silicon, but then his techniques where he goes beyond the atomic resolution, even able to see structures within an individual atom, seeing the distribution of electrons in single atoms, which is quite extraordinary. Again, very few people are able to do that. And that's gone on to more recently looking at individual organic molecules, such as the famous pentazine images, where you're able to create images that look so much like the molecular models that you see at school. So things continue to develop. So in atomic force microscopy, there are two limitations. One is that you want the force to be as low as possible, and so non-contact techniques have been developed. And the second is the process of imaging is quite slow. And so to increase the speed is an important aspect, especially when you're trying to look at processes. Maybe it's a corrosion process in material science or a biological process at the molecular scale. And so this has also been going on in parallel, that people have been trying to increase the speed. Initially Paul Hansma was doing this, and more recently, over the last, probably 15 or more years, Toshio Ando in Kanazawa University has really refined this technique of high-speed tapping mode images and seen some quite remarkable molecular processes going on. Of course, we've also been involved in this area doing high-speed imaging in a very different way, and we want to develop our current technique of high-speed non-contact. And I think the challenge here is to go from individual molecules to looking at living cells and looking at processes occurring on living cells, ion channels and proteins entering and leaving the cell membrane. The membrane is a very dynamic structure. But to do this, we'll need to develop techniques that are able to image surfaces that have higher topography than those that you contend with when you're looking at individual molecules. But this would really open up the field for biological sciences, I think. Okay, so high-speed, non-contact imaging at on living cells is what we're trying to do in this lab, which is in the Nanoscience and Quantum Information building in the basement, in one of the quietest places in the world. This slab that the whole apparatus is sitting on, and there we hear the air jacks readjusting to keep the slab level, produces the quietest, lowest vibration environment anywhere in the world. This is a prototype made by Rob Hardiman during his PhD of the high-speed vertical probe microscope. So most AFMs use a cantilever that's almost horizontal. In this case, the cantilever is completely vertical, perpendicular to the sample. And this allows us to approach the sample and sense it through the water structure before we touch it. So we put essentially zero force on the sample, allowing us to look at very delicate samples and not influence processes that might be occurring, say, on a cell membrane. So our goal is to use this microscope, which is a high-speed version, to image the surface of cells.